Hello, everyone. Let's dive right into the world of triangle similarity. Have you ever noticed how different sized versions of the same object, like similar buildings or scaled up toys, have the same shape but different sizes? Well, that's what we are exploring today with triangles. So, what does it mean for two triangles to be similar? In simple terms, two triangles are similar if their corresponding angles are equal and their corresponding sides are proportional. Have you ever wondered how we can know when two triangles have the same shape even if their sizes differ? That's exactly what the AA or AA Criterion helps us determine. If corresponding angles of two triangles are equal, their sides are proportional. This means the triangles are similar. For example, if we have triangle ABC and triangle definite, we can write this as delta ABC is similar to delta definite. The key idea here is that the corresponding sides of the triangles will follow a proportional relationship. Now, how do we prove this? The proof uses a construction of triangle DPQ that is congruent to triangle ABC, and we also know that PQ is parallel to EF. This construction shows that the corresponding sides of the two triangles are proportional. We also use the angle sum property, which tells us that if two pairs of angles are equal, the third pair must also be equal, ensuring the triangles are similar. In simpler terms, angle equality alone is enough to ensure triangle similarity. As long as the corresponding angles are equal, the triangles are similar and their corresponding sides will be proportional. Welcome back. In this scene, we are going to explore Theorem 4, also known as the SSS criterion. Have you ever thought about how you could prove that two triangles are the same shape even if they're different in size? Well, the SSS criterion gives us the answer. It says, if the corresponding sides of two triangles are in proportion, then their angles must be equal. Let's break that down. If you have two triangles, let's call them triangle ABC and triangle definite. If the ratio of side up to side A, side BC to side EF, and side CA to side FD are all the same, then the two triangles are similar. This means their corresponding angles will also be equal and their shapes are essentially identical. In other words, you could think of it like this: the ratio of up to A is equal to the ratio of BC to EF, which is equal to the ratio of CA to FD. This can be written as the ratio of side up to side A equals the ratio of side BC to side EF, which equals the ratio of side CA to side FD. Now, how do we prove this? Well, the proof involves constructing another triangle DPQ, where DP equals AB, DQ equals AC, and PQ is parallel to EF. This construction ensures that the two triangles must be similar because their sides are proportional and their corresponding angles are equal. Here's a quick insight: proportional sides guarantee equal angles. It's like when you're setting up a building with two parts that need to match perfectly. If the sides are the same ratio, the angles will align too. And that's the core of the SSS criterion: proportional sides lead to similar triangles. In real-life applications, think about how architects use this principle when designing buildings. If they use the same proportions for two structures, the overall shapes of the buildings will be similar, even if one is much larger than the other. So, the SSS criterion gives us a powerful tool to determine if two triangles are similar based purely on the proportionality of their sides. Pretty cool, right? Welcome. In this section, we are going to explore Theorem 5, also known as the SAS criterion. Have you ever wondered how we can prove that two triangles are similar by just comparing one angle and the sides that include it? Well, the SAS criterion gives us the answer. It tells us that if one angle of a triangle equals one angle of another triangle, and the sides including these angles are in the same proportion, then the two triangles are similar. Let's break this down. Imagine we have two triangles, triangle ABC and triangle definite. If the angle at A is equal to the angle at D, and the ratio of the corresponding sides, side up to side D and side AC to side DF, are the same, then we know these two triangles are similar. This means their corresponding angles will be equal and their shapes are essentially identical. Mathematically, this can be written as: if angle A equals angle D and the ratio of up to D equals the ratio of AC to DF, then we can say that triangle ABC is similar to triangle definite. Here's the cool part: the key here is just one angle and the proportionality of the sides. It's like saying, if the angle is the same and the stretch or scaling of the sides is the same, then the two triangles must be similar. Think about it like this: when you look at scaled models of buildings, the angles in both the original and the model are the same, but the size of the model is proportional to the original building. The AA criterion helps us confirm this similarity by just comparing one angle and the proportional sides. And that's the AA criterion in action. By comparing just one angle and the proportional sides, we can confidently say that the two triangles are similar. This principle is extremely useful in geometry, helping us identify similar shapes even when the triangles are different in size. Hello there, math explorers. Today, we are diving into something fascinating, proving similarity by AA, which stands for angle-angle-angle similarity. Sounds like a big term, right? But don't worry, it's actually a very intuitive concept. Let's start by imagining we are looking at two triangles where we know that one side of a triangle is parallel to a side of another triangle. Here we have PQ parallel to RS in triangle PQRST. Can you see how one side of the triangle is lined up perfectly parallel to another side? Now, let's use this to establish some angles. The angle P is equal to angle S because they are alternate angles. These angles are formed when a transversal crosses parallel lines. It's like how train tracks make equal angles with the ground on both sides. Similarly, angle Q is equal to angle R because they are alternate angles too. But wait, there's more. Angle POQ is equal to angle SOR because they are vertically opposite angles. We see how angles formed across the point where two lines intersect are always equal, just like two opposite corners of a book, always aligned. Now here comes the magic. Since we know that all the angles of triangle POQ are equal to the corresponding angles of triangle SOR, we can conclude that these triangles are similar. That's the power of AA similarity, the angle-angle-angle condition, which tells us that if three angles of one triangle match three angles of another, the triangles are similar. Simple, right? Quick insight: parallel lines and vertical angles are your best friends when proving similarity. They quickly give us what we need to apply the AA rule. And that's how you can prove similarity using AA. Isn't it fun to see how something as simple as parallel lines and angles can tell us so much about the shape of a triangle? We'll explore how to apply this concept to more complex geometrical problems. Stay tuned. Hey there, students. Let's dive into an exciting concept of finding angles using the SSS similarity criterion. Have you ever wondered how we can find angles in triangles using simple ratios? Well, today we are going to explore just that. Now, take a moment to look at this triangle example. In triangles A, B, C and P, Q, R, we are given that the sides satisfy the condition A, B divided by R, Q equals B, C divided by Q, P equals C, A divided by P. This is the SSS criterion for similarity, meaning that these two triangles are similar. What does this mean for us? It means that corresponding angles of similar triangles are equal. That's the key to finding angle C here. So, let's break it down step by step. Since triangle ABC is similar to triangle PQR, we know that angle C in triangle ABC corresponds to angle P in triangle PQR. This allows us to say angle C equals angle P corresponding angles. Now, let's move forward by using the angle sum property of a triangle. We know that the sum of the angles in any triangle is always 180 degrees. So for triangle ABC, we can use the following equation: angle C plus angle A plus angle B equals 180 degrees. Substituting what we know, we get angle C plus 80 degrees plus 60 degrees equals 180 degrees. Simplifying, angle C equals 180 degrees minus 80 degrees minus 60 degrees equals 40 degrees. Therefore, angle P in triangle PQR is also 40 degrees. And that's how we find angles in similar triangles using the SSS Similarity Criterion. Isn't that amazing? This criterion allows us to compute unknown angles in a fraction of the time. To summarize, we first identified that the two triangles were similar using the SSS condition, then used corresponding angles to link triangle ABC and triangle PQR, and finally applied the angle sum property to find the missing angle. Next time, we'll explore more advanced applications of triangle similarity. Stay tuned for that. Hey there, have you ever wondered how the height of a lamppost affects the length of its shadow as someone walks away from it? Sounds like a fun mystery, right? Let's dive into a problem where we'll use some geometry and similarity to find the solution. This is where understanding the criterion becomes really powerful. Let's break it down. We have a lamppost standing 3.6 meters tall and a girl walking away from it. The girl's height is 0.9 meters and she's walking at a speed of 1.2 meters per second. She walks for 4 seconds, so the distance she covers is, yep, you guessed it, 1.2 meters per second times 4 seconds, which gives us 4.8 meters. That's how far she's walked in 4 seconds. Now, let's look at this situation geometrically. We have two triangles here. The first one is the triangle formed by the lamppost, its shadow, and the line connecting the top of the lamp to the tip of the shadow. The second one is the triangle formed by the girl and her shadow. Now, notice this. The angle at the top of the lamppost is the same as the angle at the top of the girl's head, and both of them share the same angle at the tip of the shadow. That means the triangles are similar. Since these two triangles are similar, we can use the angle criterion. This criterion tells us that if two triangles have two corresponding angles that are equal, then their sides are proportional. So, for our triangles, the ratio of the height of the lamppost to the length of its shadow is equal to the ratio of the girl's height to the length of her shadow. Let's set up the proportion. We know the height of the lamppost is 3.6 meters and the height of the girl is 0.9 meters. The distance she walked, 4.8 meters, will add to the length of her shadow, which we'll call x. So, according to the proportion, b divided by the equals 4.8 plus x divided by x equals 3.6 divided by 0.9. Now, let's solve for x. When we simplify the proportion, we get 4.8 plus x equals 4x, and then 3x equals 4.8, which leads us to x equals 1.6 meters. That's the length of the girl's shadow. And there we have it, the shadow length is 1.6 meters. Pretty cool, right? This concept of similarity in triangles doesn't just apply to lamps and shadows, but to lots of real-life situations. Whether you're measuring the height of a tree or determining the length of a shadow cast by a building, this is the kind of mathematical thinking that makes problem solving easier and more intuitive. So, next time you're out in the sun, look at how shadows change as you move. Now you'll know exactly how to calculate their length with a little help from geometry. In the next video, we'll explore how this idea can be extended to more complex shapes and situations. Stay tuned. Let's start with a quick recap. There are three key criteria to determine the similarity of triangles AA or SSS and SAS. These criteria are like shortcuts that help us compare triangles without checking every side and angle directly. Each of these criteria ensures that not only are the angles equal, but the sides are proportional too. So, A means all corresponding angles are the same, SSS means the sides are in the same proportion, and SAS is where two sides are proportional and the included angle is the same. Here's the best part: by using these criteria, you don't need to check all 6 pairs of sides and angles. You can quickly determine similarity just by checking a few. Now, how does all of this help in real life? Let's see. Imagine you are proving that two lines are parallel. You can use the similarity of triangles to show that. Or consider the classic height-shadow problems. Using these criteria, you can find out the height of a building just from its shadow. And if you dive deeper into geometry, you'll see that these criteria even lay the foundation for more complex ideas like the Pythagoras theorem. In fact, the idea of triangle similarity comes up everywhere in advanced geometry proofs. So, here's a quick takeaway: triangle similarity criteria streamline a lot of geometry work. They reduce the complexity of proofs and help you focus on the essential parts of the problem. And that's the foundation of triangle similarity. It's not just about equal angles, it's about proportional sides and simplifying your work. Stay tuned because in the next video, we'll explore some of the cool applications of these criteria in geometry and beyond.